In this lesson, we'll work through a number of different organic families. We'll identify the features and functional groups of the families that make them part of that group, and we'll learn how to name these molecules. Your approach can be one or another. The first approach that you might take is to watch the entire video and then do the exercises that go with each of the different parts. Or you might choose to watch the video in smaller segments and do the activities after each family is discussed. Okay? The way that you do that is up to you. The first family that we'll look at are cyclic alkanes. And cyclic alkanes, as the name suggests, have all single bonds between the carbons in the molecules, but there are rings of carbons. So we've discussed one of the reasons that there are so many different possibilities for organic molecules is that carbon can form chains like we've seen before, but carbon can also form rings with itself. Now, when we form a ring with the carbon, the general formula will change. So these are actually isomers to alkenes, because for every carbon that you need twice as many hydrogens in order to ensure that all the atoms are satisfied in terms of bonding. If you look at this table of some basic cycloalkanes, what you can see from the name is that we use the prefix cyclo in order to identify that the carbons are found in a ring. The same prefixes are used to represent the number of carbons that are involved, and then the ending here, the ane, is telling us that it is an alkane. We can also have, for example, a cycloalkene, which would have a double bond somewhere on the ring. For naming cycloalkanes, there are going to be two different possibilities, and we'll look at both of these together before we name them. As you know from naming alkanes, your job is to find the parent of the molecule. And the parent might be a chain or it might be a ring. And it really depends on the length. And what we learned was that it's all about finding the longest possible parent. So when we look at a molecule, in this one here, we want to see what is the longest continuous chain of carbons. And so the longest continuous chain of carbons is this 5-carbon ring. When we're counting, we don't start outside of the ring and go through the ring and come around. Okay, that would be a chain. We either look at the ring or we look at the chain. So this here, this propyl group, is shorter than these 5 carbons in a ring. So in this case, the ring is going to be the parent. When you look at this molecule, immediately you can see that this chain is much longer than the number of carbons in this ring. So in this case, the longer chain is going to be the parent of the molecule. And we'll discuss how to name that in a moment. So as always, we need to identify the parent chain first. So here we've identified that it is the 5 carbons in a ring that are all single bonded. So cyclo tells us that they're in a ring. Pent tells us that there are 5 carbons, and the ane tells us that they are all single bonded. So this is a cyclopentane. And our next step is to identify the substituents and their positions. And just like before, we want the lowest possible numbers when we are identifying the position of the substituents. So in this case, I can start numbering this ring at any position, but in order to get the lowest possible numbers, I'm either going to call this 1 and this 2, or this 1 and this 2. I'm not going to start over here and have 3 and 4, or 4 and 5, for example. Now, the rule to decide which direction I'm going to go is going to be based on the complexity of the substituents. So the one that gets priority, and when we use the word priority in organic chemistry, we're referring to the one that gets the lowest number. The one that gets priority here is the more complex group, or the one that has more carbons or atoms in it. So in this case, the propyl has 3 carbons, so it's much more complex than the methyl, which only has 1. So this is going to be carbon 1, and this is going to be carbon 2. Like before, we need to put these in alphabetical order. So we have our methyl and our propyl. So the M is going to come first. So then I build the name here, 2 methyl, 1 N-propyl, cyclopentane. Okay, so that's how we name a cyclic alkane. Now in this one here, the parent chain is clearly the longer chain here instead of the ring. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is a decane. And then this is a group that's attached. 1, 2, 3. It's going to be on the 3rd carbon. And we build the name the way we would expect. So cyclo tells us that it's in a ring. Bute tells us that there are 4 carbons. And because it's a substituent, just like above, it ends in YL. So 3-cyclobutyl decane. So at this stage, you can, if you would like, do the exercises on page 11 and 12. The next group of molecules that we're going to look at are referred to as aromatics. And we're going to focus on one particular type of aromatic, which involves a molecule that we call benzene. So when we look at this molecule, this is benzene, and it's got a chlorine attached to it. Okay? And there are 3 different ways of looking at benzene here. So essentially what it is 6 carbons in a ring with alternating double and single bonds. And there are 6 hydrogens attached to ensure that each carbon has 4 bonds. Now, at first glance, you might think to yourself, well, why isn't this part of the alkene family? Because it has double bonds in it. And one of the things that puts molecules in a particular family is their similar properties. And one thing that chemists observed is that benzene and these molecules that we refer to as aromatics, although they have double bonds in them, they don't actually react in the same way that alkenes do. Alkenes are actually quite reactive and easily react with things like chlorine and bromine and iodine, whereas benzene in the same conditions doesn't tend to react with these things. So they've been put into 2 separate families because they have properties that are different from one another. Now, the reason that benzene behaves in this way comes down to its structure. It's a much more stable structure, and you actually have the knowledge in order to understand this. Because when you look at this molecule, what you might observe is that there could potentially be a resonance structure of this. So these double bonds could actually resonate between the positions 1, 3, and 5 and 2, 4, and 6. And as you know from resonance structures, when we look at this, then the bonds in this molecule are actually all the same length. Okay? So if we compare here, this is a single bond in an alkane, has a length of, on average, 1.54 angstroms. And angstroms are 10 to the minus 10 meters. Double bonds in an alkene are 1.47 angstroms. And because of this resonance, we would expect, and in the last unit, we would have discussed the fact that, these bonds will be somewhere in between that of a double bond and a single bond. But what we observe in benzene is that actually the bonds in benzene are even shorter than a double bond. And they have a certain special stability related to them. We're going to look at that idea even closer when we look at hybridization in a couple of lessons. So we'll really understand what it is about the bonding in benzene that it is making it resistant to reacting and also making the bonds so short. For now, what we need to do is just recognize that it is a 6-membered carbon ring with alternating double and single bonds. And if we were to name this just as an alkene, what we would do is we would call it 1, 3, 5 to identify the positions of the double bonds. Cyclo, because its carbons are in a ring. Hex, because there are 6 carbons. Hexa, and because there are 3 double bonds, we say tri-ene. Okay, the ene telling us that there are double bonds. Now, this is quite a complex name, and for something that is so common, what chemists have done is they just call this benzene. So rather than calling it 1,3,5 cyclohexatriene all the time, we just call it benzene. So let's look at the naming. So just like with the other cyclic carbons, we can have the benzene as the parent, where it is the longest chain, or we can have it as a substituent. When we identify it as the parent chain, we simply call it benzene, and then the naming is going to be the same as with the cyclic alkanes. So we identify the groups that are attached. We give priority to the more complex group. So in this case, the methyl has CH3, so that's got 3 atoms in it. So this is going to be 1, and this is going to be 2. And then we put it in alphabetical order. So 2 chloro, 1 methyl, benzene. Now, for now, we'll leave it at that. There's also an older naming system that we'll discuss at some point. Okay, but doing the standard IUPAC method of naming is fine for now. Now with this one, you identify here 1, 2, 3, 4, 5, 6, 7. This is actually my longer chain. So this has basically been downgraded to a substituent. Okay? So although it looks really special, benzene is not that special. So this is a heptane, and we want the substituents to have the lowest numbers. So this is going to be 2 and 5. Okay, so it's not like with this one where it was the more complex group that gets the lower number. Remember, when you're naming an alkane, it's about the lowest set of numbers. And if we numbered going the other direction, we would end up with 3 and 6, which is not as low as 2 and 5. Now, this group, when it's attached, okay, we call it a phenyl group. So P is going to be used for the alphabetical order. So in this case, we have 2 methyl, 5 phenyl, heptane. So at this stage, you could do the exercises on page 18 and 19 involving naming and drawing aromatics. Now, at this stage, we've covered all of the hydrocarbons, the molecules that are made up of carbon and hydrogen. And now what we're going to do is introduce molecules that have oxygen and nitrogen in them. And we're going to look at these in pairs, and I'll explain that, why we do that. So the first pair that we look at are alcohols and ethers. And these are actually isomers of each other. So if I have a formula, I could draw an alcohol with that formula, or I could draw an ether with that formula. And these have all single bonds, and there's an oxygen in them. The next pair are aldehydes and ketones. These are also isomers of each other, and they have a functional group that we refer to as a carbonyl, which is a C double bonded to O. The next pair are carboxylic acids and esters, and they are isomers of each other, and they include what we refer to as the Cu group, or C double bonded to O and single bonded to O. And the last grouping are amines and amides, and these aren't isomers of each other, but they're paired together because they both include nitrogen. So the first pair that we'll look at are alcohols and ethers, and you're on page 21 in your package. So alcohols have a hydroxyl or an OH group as their functional group. And the location of the OH will help us to identify whether an alcohol is a primary, secondary, or tertiary alcohol. So to identify whether it's primary, secondary, or tertiary, what we do is we look at the carbon that is holding the OH, right? So there's no carbon in between the O in that little space. This O is attached to this carbon. So this carbon here that's holding the OH has one other carbon bonded to it, so it is a primary alcohol. A secondary alcohol, the carbon holding the OH has two other carbons attached to it, whereas a tertiary alcohol has three carbons attached to the carbon holding the OH. So one of the things that you'll practice doing when you're naming them is identifying whether the alcohol you're looking at is primary, secondary, or tertiary. So naming an alcohol. Now, in all of these families that we're going to look at, the naming really comes back to how to name an alkane. So our first step in naming an alkane, and therefore with any other molecule, is to identify the longest continuous chain of carbons. Now, because we have a functional group, just like with alkenes and alkynes, that functional group needs to be part of our longest chain. So here we have 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So we need to take this route going through, because even though both of these have 7 in them, we need the OH to be part of the longest chain. Okay, so my parent chain is 1, 2, 3, 4, 5, 6, 7. Now what we do with these, anything beyond hydrocarbons, the strategy for naming them is to take the alkane name, so in this case it is heptane, and we're going to drop the E and add our new ending. So for an alcohol, the ending for the parent is going to be -ol. So we're going to call this heptanol. So we take the alkane name, drop the E, and finish with OL. Now we need to tell people where the OH is, and then we also need to identify the substituents and their locations. And the key with anything that has a functional group is that the functional group gets priority or gets the lowest possible number. So here, the OH is, or the hydroxyl group is on carbon 2, and so I number the other groups accordingly. Here I've got an ethyl group, and I've got 2 methyl groups, so my ethyl is going to come first alphabetically. So I have 3 ethyl, 4 dimethyl. Remember, you have to put the prefix when a group is repeated. So 3 ethyl, 4 dimethyl, 2 heptanol. To identify whether this is primary, secondary, or tertiary, I look at the carbon holding the OH, and I count how many carbons it has attached to it. So this is a secondary alcohol. So at this stage, you can complete the exercises on page 22 and 23. Now with ethers, which you'll find on page 24, they are isomers of alcohols. And so what that means is that if we're given a formula, so let's work with this one here. I've got this formula, and let's just practice drawing it. I've got CH3, CH2, I've got an O, then I've got CH2, CH3, CH3. Okay. So this is not an alcohol because it doesn't have an OH in it. What an ether has is it has a single bonded O somewhere in the middle of the chain. I can take this exact formula and I can turn it into an alcohol. So I can put an OH on the end, and I will end up with the exact same formula. So 1, 2, 3, 4, 5 carbons. The number of H's, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is the formula, and if I examine this ether, it's the exact same. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 1 O. Okay, so you can see that they are isomers of each other. They have the same formula, but a different structure. Now, we're not going to learn how to name them. We don't really work with ethers very much in high school chemistry, and so we don't really need to identify their naming. It's just more rules, and we like to focus on the molecules that we'll be using down the road, especially when we study reactions in grade 12. So for now, you need to identify them, recognize that it's an ether, be able to say that it's part of that family, and make isomers, which is the practice that you'll do on page 24. Our next pairing, and our last one for this lesson, are aldehydes and ketones. And aldehydes and ketones are isomers of each other, and what they have in common is that they have a carbonyl group, which is a C double bonded to O. So when you look at the expanded molecular formula, if you're drawing an aldehyde, right, this one here, 1, 2, 3, sorry, this is actually belongs here. So yeah, you have a CHO at the end. So if you do that, CHO, what you'll see when you do that is that the carbon only has 3 bonds and needs 4. The oxygen only has 1 bond and needs 2. So that's how we know that there's a double bond there. Now, both aldehydes and ketones have this functional group. The difference between them is that in aldehydes, the carbonyl is at the end of a chain, whereas in a ketone, it's somewhere in the middle. And right now, that's going to seem like a really unnecessary difference between them. But again, we classify things based on having properties in common. And when we look at reactions later on in grade 12, we observe that aldehydes and ketones react differently. The position of the carbonyl actually affects how these molecules are able to react. Okay, so naming an aldehyde, okay, same thing. We need to identify the parent chain. So the longest continuous chain of carbons, 1, 2, 3, 4, 5, 6. We need to be careful. There's no carbon right there. This is just showing the H that's attached. It's often shown. It doesn't need to be shown. It's often shown just because of reactions that we observe with aldehydes. Okay, but this is carbon number 1 here. So 1, 2, 3, 4, 5, 6. So again, we're going to take the alkane name, which in this case is hexane, and drop the E. For an aldehyde, the ending is AL. So this is hexanal. Now with aldehydes, we don't need to tell people where the carbonyl is or the functional group is because the name tells us. Right? It's an aldehyde, and so the C double bonded to O is at the end of the chain or on the first carbon. I do need to state the location of the substituent. So this is carbon 1, 2, 3, 4. So this is 4-methyl hexanal. And at this stage, you can complete the exercises on page 25 and 26. Ketones, as we've discussed, the difference is that their carbonyl is somewhere in the middle of the chain. So it's basically not on carbon number 1. But the naming is the same. Step 1 is to find the longest continuous chain. That includes the carbonyl. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so this going through here is our longest chain. So we take the alkane name without the E, so heptan. Ketones end in -one. So this is a heptanone. In this case, because the carbonyl could be anywhere along the chain except for on carbon 1, we need to state its position. So 1, 2, 3. So this is a 3-heptanone because the carbonyl is on the third carbon. These groups here, I have an isopropyl, and I've got a methyl. Alphabetical is based on the number of carbons in my substituent, not based on any prefixes. So the methyl is going to come first. That is on carbon 5. So I have 5-methyl, 4-isopropyl, 3-heptanone. And make sure you're including dashes between the numbers and the letters. So at this stage, you can complete the exercises on page 27 and 28.